Hello? We're late. It's not my fault though. I was here on time. Let the record show. Yeah, so if we want to fix the crash, so here's the crash, right? Because we're dereferencing the follow actor to get its actor location. And of course, unlike in Unity, where it has this whole scripting layer on top of its actual engine, like the engine is running C++, but then they have the scripting layer on top of that, where they can handle crashes and all of that stuff. Like they can just handle that, and just shut down the game or give you an error or something. In Unreal, of course, we're writing everything on the same layer as the actual engine. Like we're all in C++ together, which means that if we do something bad, like if we dereference a null pointer, the engine will crash. There is just because there's no way to recover from that in that case, because we don't have that sort of protective layer of scripting. So that means we have to be careful when we're dereferencing pointers, just to make it not crash. And in this case, it's quite easy. We can just do like if follow actor is null pointer, then just return. You just don't do anything. So that was pretty easy. Can't believe we didn't figure that out, Ruth. That was so easy.
I didn't wanna.
You didn't wanna?
Yeah.
Enough. I respect it. Yeah. So that's how we would. Fix that bug. So that's good. All right. Bug fixing out of the way. What's up on the shopping block? So if I put a cube here, if I just drag a cube from the place actor here, the actor picker, let's put that in there. Right now, we're just gonna go right through it, right? Because we don't have any... I can't tell if the steering is wrong or not. Like when I'm... It is wrong, yeah. Yeah, our steering is wrong. Because when I'm backing up and I'm holding right, this is not what I'm expecting to happen. So we're gonna have to fix that at some point as well. I got a bit messed up by that. Okay, so yeah, so if we go through this, we'll go through it. So we don't have any collision checking, right? We're just setting the actor location, which doesn't do any sort of collision checking on its own. So let's add that then. We're just gonna use the same thing we did for the projectiles in when we did when we just fucked around before. So we want to make it so when we're moving, we're not just moving, like just setting the actor location, right? Because that's what we're doing now. Like we're here, and then we're setting the location to be here. Instead, what we're gonna do is that we're gonna sweep. So again, just a reminder, a sweeping means... So if we want to sweep from here to here, a sweep means that I will do a continuous checking. So this whole area here will be checked in between these two boxes. This means if there's anything in the middle, it will be colliding with that. So we can't tunnel through walls, we can't do anything like that. And the good thing about sweeping is, of course, we'll get sort of the location of the sweep. Like, we hit here, for example. It's like, okay, that's where we hit the wall. And we get all this kind of nice, juicy data out of it. Very nice. So what I'm going to do, I'm going to hop into the moving component. And then here where we move, where we add actor world offset, we have some additional parameters, right? We have bsweep. So I'm just going to turn that on. So bsweep is true. So now we're going to be sweeping whenever we move. And ain't that just dandy? I should turn off symbol loading really, because it kind of slows down our start a little bit. Actually, I will turn that off. I'll show you how to do it. Go into Tools, Options, Debugging, Symbols, and we're gonna do Load Only Specified Models. Modules, sorry. I've actually unchecked this as well, because that will actually take a bit of time to load, like NTDLL and R of the standard C compiler symbols. So just check that off, so it doesn't load automatically. But yeah, so then load only specified modules. Okay. So now our starting time should be just a tiny bit quicker. And we can always, of course, just load the modules if we need to debug them. We can just load them whenever that happens. So now, when I go into this guy, it doesn't work. We just go right through him. Can anyone tell me why?
Because we're just sweeping. We're not doing anything else.
That's a good guess. Although sweeping should stop us at the location. So when you're doing a move with a sweep, it will actually move up until the hit and then stop there. So a good guess, but no.
Is it because we're not changing the velocity? Even if we hit something, we still try to...
Good guess as well. Sorry I cut you off rudely, that was rude. Good guess as well, but no. We should still just go up to the cube and stop. Well, collision preset, very good, Anders. Yes. We added a box component to our... Oh god, excuse me. Oh. We added a box component to our car. Box collision here. But of course, a box collision, or not of course, I'm telling you, the box collision has by default overlap all dynamic. Which means that it's not blocking on anything. And of course, a sweep will... I'm saying of course a lot, like this shit's obvious. It surely is not. Naturally, I can't think of a better adjective, whatever. Naturally, the sweep will only stop if a blocking hit was happening. So it does not care about overlaps. Overlap, it will just keep tunneling through. It doesn't care. Isn't that the song from the Jungle Book? No, but yeah. So it will just tunnel through overlaps, but it will stop when it hits something blocking. So we gotta change our box collision here so that it reacts blockingly with everything. I don't think that's a word, blockingly. We could do it in here, and I probably would, honestly, if this was a real game. I probably would go in here and just select block all here, because it's just kind of much easier to work with collision presets in Blueprints. But I will show you how to do it through code, so we can set this as a default block all. Just so you guys kind of know how to do it. So we're gonna set that as default on our car. So I'm gonna go into race car here. And here where we make the box collision, I want to set the default collision profile to be block all dynamic. So we're gonna So we're gonna do in box collision set collision profile name. So this one provides a profile name. So that could be any one of these collision presets. So we could do pawn or vehicle or UI and so on. Could do that. Or we could go in and manually set just what the collision profile should be by doing set response. Set collision response to all channels. We could also do that to tell it like, hey, I don't want to give you a profile. Like, I don't need, maybe you don't have a profile that fits exactly what you're trying to do. And you just want to say like, okay, I'm just going to manually set what the response should be to all channels. So that takes a F collision response container. I have no earthly clue what that is. This is not what it looked like before. Oh, you know what? I think there's another function I'm looking for. Yeah, there we go. Okay, this was the one I was looking for. Set collision response to all channels. Okay, sorry. So this will set the same response to all channels. The one I was on, 2 channels. Here you can specify each channel individually. So here you would specify like, okay, for world static, then block. For world dynamic, then overlap, and pawn ignore. So you like sort of fill these in through code. But we want to set everything to block. Like, we don't care. Everything should just be block. So then we want to use this set collision response to all channels. A profile is like one strip from a Unity collision matrix. Not really, no. A profile is more like a preset of all of these values. So a profile is never really like, you can't set like, okay, how should an object react to spectator, for example. That's not a part of this matrix. Spectator is just a default profile for how a spectator should react to other objects. So you can see as I'm changing this preset here, you can see all of these settings change to whatever you set this trigger preset to be. So that's all that is. It's just a template essentially for different collision settings. You can add them yourself if you want to, or remove the ones that are here. Let's revert that. But okay, so we want to set the response to all channels to be blocking. So we're gonna do ECR block. So Unreal is a little bit inconsistent with their enums, unfortunately. Some are enum classes, and some are not. And this one, I believe, is not an enum class. No, this is just a regular enum. So that means we have to just type out ECR underscore overlap block and so on, and not collision response : : we have other ones like this one, where they actually write, they wrap the enum in a namespace. So this is kind of how you would do enum classes before enum classes existed. So to use this world type, you would have to type like, you know, e world type inactive because of the namespace. But then if you wanted to refer, like if you wanted to take a e world type in as a parameter somewhere, like if we made a function, like void set world type, then you would write like e world type : type, like that, because that's the actual enum inside of the namespace. So this is how you would refer to this, the enum type. You would write this : type. Very hacky. I don't like this, but yeah, I mean, whatever. I'm guessing this was before enum classes. And then on here, it's nice. We have actually every example in just one file. And down here we have enum classes. So here they're using an enum class. Usually they use the uint8 type override for the enum. So these just work like a regular enum class. So here you would just type flush level streaming type full. And to take a type as a variable or a parameter, you just write the flush level streaming type, like so. Yeah, so if you see an enum, make sure to go look at it just to see like which kind of enum it is. If it is an old style, like a C style enum, where you have a prefix, or if you have a namespace type enum, where you have a namespace and then a type inside of it, or if it's an enum class. Those are the 3 main ways that Unreal does enums. Nowadays, like if you're making a new enum, the standard is to make it an enum class. That's sort of became the standard nowadays. But especially if you're looking at a little bit of older code, like now we're looking at collision stuff, then most likely you'll see stuff like this, where you have old C-style enums. Mm-hmm. When we create enums, should we use enum class? Most of the time, yes. I would say 95% of the time, yes, use enum classes. Unless you're planning on doing some weird enum math on it, like using them as a bit mask or something, then it could be nicer to just make a regular enum. They both work as far as they all work as far as, you know, mapping to the engine. Like they all can be parsed for the engine, so it doesn't really matter which one you use. But yeah, what were we doing? Oh yeah, we set the we set the collision profile, right? That's what the goal was. So let's go and see. So if I click the box collision here on the car, yes, so now we can see we have a custom collision preset. So that simply means like we have changed the matrix outside of some preset, so that makes it show up here as custom. And we can see that everything is block, so that's good. So our default setting that we set from C++, where we set the collision response to all channels to ECR block, seems to have worked. So now we have an all blocking box collision here. So that's great.
But that's just like you've now set it as default, so you could still like change it in the blueprint.
Yeah, we can still go in here and change it, right? But what's nice about setting it as default from C++ is that if we just hit this like reset the defaults, they will go back to being blocking, which is quite nice.
Okay.
But yeah, you can still override them as much as you want. So yeah, I would probably have gone into blueprint and you set it to like set the collision preset to be like block all dynamic or something. But it is good because sometimes it can get you out of a pinch to know just how to do it. So C++, like sometimes you need to do it. But yeah, in general, I set those things from blueprints, but that's just me. So now we should have a blocking volume, which means that if we put a cube in here, we should not be able to go through it. Let's see. Let's go! Okay, great.
Could you show us how you did the sweep again?
The what?
Sweep. You said you...
Yeah. Here, I just put true after the world offset delta. So that's the pool. Let's say it should be sweeping. Sweeping ding. Okay, so now we have sweeping. Oh, good, great sweeping. You tell me your truths of life. So now we have some basic collision going. It's not great. I haven't really played a racing game where if you crash into a wall, you're stuck. Not very nice. And for those who remember the SDL course or the SDL lectures that I have, this is very similar to the bug we had when we did collision there, remember? That like, you couldn't run up against a wall. It was always like, if you ran into a wall, then you got stuck, at least in the beginning, then we fixed it. And that's that's a common problem, like even in 3D, right? Where you have to kind of resolve the collision to be like, okay, we can't move there, but where can we move? Like, what do we do after we hit here? And in 2D, we had quite a simple solution using AABBs, if you remember. Like, we made the assumption that in case everything in the level is always axis aligned, then we could assume that if we hit something, it's like, oh no, I hit something, I hit the wall. Then we would assume that we would only hit it when going in one direction. Like either we would hit it when going in Y, or we would hit it when going in X. So when we split those two moves up, then we could still move along wall. So even if the Y collision sort of happens, or the Y position, the Y delta sort of got negated, the X position could still keep moving just fine. So we could still slide against walls. Yeah, I think the problem you're having, Alphonse, I can't move, but I can build up velocity once I enable sweep. When I set the collision channels to ECR block. Yeah, I think your problem is that your car is actually clipping with the ground a little bit. If I do this, then now I can't move either. So yeah, just make sure to move it up a little bit from the ground. I just hit end, and apparently that was precise enough that I could still move on the ground. So maybe do end, so then you'll know it's just high up enough that you'll be able to move. But yeah, so that was the solution we did. Very simple, and I like that. Of course, we're not working with AABBs anymore. Unfortunately, I wish the industry would have stayed with AABBs. I don't think you need anything other than AABBs. It's just overcomplicating things. But obviously nowadays we can have a cube that's rotated in any way. So even though we sort of come up at it like this and hit the wall, we want to slide sort of diagonally like this. Like we want to slide diagonally against the wall. Oh, BB cringe. Which is obviously a little bit more complicated. Like how the fuck do we do that? So not great. So we need to be a little bit more sophisticated in our collision resolving, and just to show that, right, I can just rotate this anyway, right? So do a weird ass rotation. So yeah, it doesn't matter where I hit it, I will still always get stuck, and there's no obvious way out. Or I say that, but there actually is. So what we're gonna do, Smith's a little bigger. A bit big. Okay. So what we're gonna do is that we want to try to figure out what this remaining velocity should be after we have a hit. So we're running up against the wall, and we want to figure out, okay, but how much is left after we hit the wall? And we're actually gonna do something very similar to what we did with the grip. Is that we're gonna break this vector up. We're gonna break it up and figure out from there. So if we have our car, so here's our car. It's coming in here. A little bit closer, please. Good enough. And it has some velocity here. What we want to do is that we want to break this velocity up into what part of the velocity is pointing towards the wall. So it'll be something like this. Like that. So here we have some velocity that's pointing towards the wall. And that's the velocity that's going to be taken out, because we can't go that way. There's a wall there. It's dangerous. Can't go there. So we want to take this velocity away. And what we want to be left with, it's just the velocity that's pointing alongside the wall. Because that's free to move space. That's free real estate. So we're going to split it up again into sort of this perpendicular pair. Where we have the part that is pointing towards the wall we should kill. And then the part remaining will be sort of our velocity after the hit. And I like to call this hit resolution. I don't know if that's the real name. Whoops. Or we also call this redirection. redirection. Because
Will this make it so we can slam into the wall at a diagonal angle like a go-kart and just keep going?
yeah, hopefully that's what will happen. Like a go-kart, is that what happens in go-karts? I feel like if you hit anything, the go-kart explodes. So the reason we call this redirection, of course, is because your direction has changed. So like you went from going in this orange direction, to this blue direction. So we redirected you so that you're going in a path that doesn't have any collision. Redirection. Cool. Yeah, so we want to take out the part that's pointing in towards the wall. Does that mean we can add wall runnings with this? I mean, you can add anything. You can yeah. I mean, this is I will say this is the basics. This is not just car. This is just like, this is the basics of movement code. Like when we did the movement for It Takes Two, for example, which is a platformer, we spent so much time on exactly this. Like, if we have a hit, how do we resolve that hit? In our case, it's gonna be super simple. We're just gonna slide against the wall. But in It Takes Two, it's a lot more like, okay, did we hit the ground? Did we hit the wall? Did we hit the ceiling? Are we going into a wedge? Like, there's so many edge cases that we have to take into consideration, and it all kind of went into this redirection code. And then we also have stuff like step downs and step ups and blah 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 and all that shit. But it's a huge topic. But that's why I like doing it with a car, because it's so simple, especially when it's just 2D on a flat plane. It's just go forward. It's quite simple.
What's a step up and a step down?
I can mention this quickly. Step down is just when you're like, here's the character, and you're on a little ledge, like this. When you walk off this ledge, you want to go down to the lower part and snap there. So you don't want to be like airborne for just a brief second before you fall onto the next ground. You just want to, as soon as you go off this, you're going to snap down to the ground and keep going. So that's step downs. And step up is just the opposites, where if you're going from the floor here and you run into a ledge, you want to go up the ledge and go to the floor above there. So that's a step up. Yeah, there's a lot of fun things there. But we're not gonna do that. Our car is not gonna step up or step down. It's gonna drive. Yeah, so we want to do this redirection. So what we want to do is that we want to split up our velocity vector into what of the velocity was pointing towards the wall and therefore should be eliminated, and what part was pointing away from the wall, or rather alongside the wall, and should be kept. So let's do that. So in our add actor world offset, in our sweep, I want to fetch out what the hit was. So here we have the out sweep hit result. So that's the hit result of whatever the sweep was hitting. That's a pointer output, so we have to make the output holder here. So we're gonna do hit results, hit, and then it's gonna pass in a pointer to that. So the result of the sweep will be written to this hit pointer here, or whatever the pointer is pointing to.
Wait, what's the difference between hit result and F hit result?
Yeah, the difference is that hit result doesn't work. It has to be F hit result. Thank you.
But it says it takes a F hit result.
Yeah, I know. I fucked up. It should be F hit results. Yeah, I'm stupid.
Okay.
I'm sorry.
Okay.
Don't be mad. Okay. So now we can check. Okay, was the hit? If hit be blocking hit, Whoa! Redirection time. So if B blocking hit is true, again it's a bool, that means we hit something on our way.
Is this kind of like a sweep?
Oh, sorry.
Is this kind of like a sweep?
This is a sweep. It's exactly a
block.
sweep.
Yeah.
All right. So, when we hit something, we want to figure out what do we want to take away. And actually, we can even take a shortcut where we don't even need to calculate this vector. Because remember, we did that before here, where we sort of projected the velocity onto the owner's to actor forward vector, and that was the rolling velocity, and then we figured out the grip velocity from that. We don't even need to do this, because we can do a shorthand. We can do velocity project onto normal. Wait, no. No. Project. Oh, it's called vector plane project. Oh god, excuse me. And that's a static function. Why did they do this? Okay. Okay, never mind. Okay, so we're not gonna do that. We're gonna do f vector plane project. There we go. So projecting to a plane. These are extremely common function, by the way. I will say that. These are like, you know, every day we would use these functions for everything. So I would recommend paying attention. Because I know you're not paying attention normally. So projecting to a normal, or sorry, projecting to a direction means if we have two vectors, right, pointing in two different directions. So if we have A and we have B, then projecting A onto B means essentially find the closest point on B and get a vector to that. So projecting A onto B means you'll get a vector that is on the B line. On the B line. Sounds pretty funny. So if this is like the B line, you know, every point that B can sort of that aligns with the direction of B. Find the point, the closest point on the B line from A, and then just return the vector to that point. So that's projecting A onto B. And this will always be 90 degrees. So you'll get a vector that lies on the B line, that it's the closest point from A. So that's projecting onto a direction. Write this in blue. Project to direction. And if you want to be fancy, this would be B times B dot A. So that's the equation, but yeah, we usually don't write this. We usually do some sort of projected direction.
Is that the multiplication or a dot product? The dot.
This is just the multiplication, and this
the
is
one in the parentheses.
yeah, and that's dot. It's a dot product. What are those duck beaks? Oh, you mean the arrows? That means it's a vector. I usually draw the arrows like this. I think Freya does like an actual arrow like this. But I usually just draw them like this. Doesn't really matter. Okay, so let's predict the direction. Okay, guys, fucking. I told you to pay attention and not to focus on the duck peaks. Okay, and then we have project a plane. So here we have some plane with some normal n. That's a unit vector, so I'm drawing that with a hat. So n hat means it's a normal vector. Then we have some vector v, just any vector. And projecting onto a plane means find the closest point. Find the closest point on the plane and draw an arrow to that. So you will get the closest vector on the plane from V. So you sort of squish it down onto the plane. So that's project to plane. And the equation for that, for those giga nerds out there, this is gonna be V minus N times N dot V. And you can actually see that this equation here is exactly the same as here. And this whole equation is actually the whole equation we did here. Right? We projected velocity onto the forward vector, which is this equation. And then we did velocity minus that projected vector. Oh, I'm gonna be on YouTube, guys. I'm famous. Exit. And of course, that's this equation here, V minus the projected vector. So we already have done a plane projection. We just kind of did that part manually. So we're fucking experts already. I don't know why I'm spending time cleaning this up, but I'm gonna take a screenshot and send to Freya and tell her I'm better than her. You guys have to play along. Okay, I'm proud of this. Look at these graphics, dude. They look fucking great. Look at this plane. Oh, mwah. That's fucking awesome. That's fucking awesome. All right. Anyway, so now that we're experts on plane projections. Yeah, I'm the live action adaptation that everyone hates. Except the people who haven't seen the manga. I'm getting distracted. So a vector plane project, we want to do that. Because, of course, that kind of makes sense, right? If we have a wall. If we have a wall here. Here's our wall. And here comes our car. Beep, beep. Dude, I'm so fucking good at drawing. Holy shit. I'm like actually peaking right now. So if we have a... if we're going through the wall here, right? Look, I'm gonna even do this fucking... Look at this. See that? Like it's going through the wall. Holy shit. Yeah, so if we have an impact here, right? Impact. How did you do the dotted line? I just fucking smashed my fucking bottom. These fucking paint strats. Yeah, so we smashed the wall here. And of course, we want to find what the velocity going alongside this wall is. So we're gonna have the normal vector of the wall. Like that. So if we just project our velocity onto the wall, then we're gonna get something like this. Where, you know, the normal and the new projected velocity are gonna be at 90 degrees to each other. So it's gonna run alongside the wall. Can you show the RGB used for the yellow? I'm pretty sure it's like 255 yellow. It's like fucking like bright yellow. So yeah, so that's what we're gonna do. I've spoken too much, let's just do it. So we're gonna project the plane, the velocity, and we're gonna project it onto the plane normal, hit normal. Your paint file, name every color. And that's gonna be our new velocity. So that's it, that's all our redirection code. It took us like, what, like an hour to get there? I'm sorry, I got into fucking this paint mode and I had to paint. You're not very understanding of my passions. So hopefully this should work, I guess we'll see. Paint. And then we'll take a break. Man, I swear, if this was like FG20 and I was in real life, they would be slaying with laughter. They would be like, ha ha ha! And then one guy would come up to me like, Emil, you're my favorite teacher, you're so funny. And I would be like, I know. Okay, so if I run, oh fuck. So if I run into this wall, well, clearly it doesn't work. So fuck. Ass. Titties. Okay, so that's not good. Maybe if I release? Nope. Well, okay, I'm not perfect, guys. All right, fucking, I didn't ever say I was perfect. All right, so you guys need to fucking back off. So clearly, it's a little bit jank. Sometimes I can kind of break myself loose, but clearly it doesn't work as expected. So we're gonna take a break. I'm gonna just really quickly just go into my mirror and look myself in the eyes for a few minutes, and then we'll continue after that. All right. So take 10 minutes. So 14:10. I'll see you guys back here. I'll show you the code while it's away.
wicked night of Halloween.
Hello?
Hi.
Hi? But are we in the ocean? Ha! That's a Swedish joke. True wide. He is the wide boy. Alright, let's continue. Last stretch before the evening. I've had a ritual these past weeks actually that after every lesson I take like a 1 hour nap, which has been quite nice. So that's why I like when you guys are asking questions after the lesson, I just don't answer for an hour. It's just because I'm fucking dead asleep. It's been super nice.
So that's why the answers take a while after the lesson.
Yes, it's the true old man energy. Just go sit in my armchair and just watch football and sleep.
Damn, you're younger than I am, so I don't understand.
Yeah, I got the old man energy already.
True old man energy is lying on the wooden couch.
The wooden couch, is that what old man does? Should get one of those. Yeah, I used to sit on my porch with my rifle, watching the neighborhood. All right,
Smoking a pipe.
smoking a pipe. Yes, it's a
Bless you, Alvin.
Thank
what?
See him sneezing violently through the webcam.
Oh, sneezing violently in the back rooms. All right, so we're gonna make this work, huh? What do you guys think about that? You want to make this work?
Yeah,
Yeah.
sounds good.
Thank you. Okay, so
Kind of.
yeah. So, oh yeah, Kronblom. This was some fucking that. Yeah, that's fucking tight ass comic strips. Yeah. So there's a problem here. It's actually a few problems, but the one that's actually causing us some issues right now is that we're only checking once for collision per step. So what's happening is that, sure, we let's give a top-down example because that's going to be easier to look at. So we're moving, right? Moving along. So even though we're supposed to move a lot this frame, let's say this is like our frame movement, all right? Frame movement. And the problem is that, okay, we gotta hit like almost immediately. We're supposed to move this whole distance, this frame. Like that's what it's on our agenda, this frame. And we only moved like a little bit before we hit the wall. So like maybe we moved up here. And then once we got to this point, then we started colliding with the wall. And then the problem is that we only do that once. Like we add active location, or add active world offset, sorry. We hit, we redirect the velocity, and then we stop. Then it's like, the frame is done now. Even though we have this whole chunk of movement that we did not account for this frame. Like we were supposed to move a lot, but we moved very, very little. And why is that a problem? Why does it matter? Like can't we just move that the second frame? Well, the problem with that is, so you know, our velocity gets redirected. So now our velocity is pointing something like that. And that's all fine and dandy, you know, that seems good. And we just move next frame. Well, the problem with the next frame is that we're still holding forward. Let's say that. I'm still holding W. So I'm still accelerating. Let's move this a little bit so it's actually right up against the wall. So we moved it there. And then we're supposed to move this. And I'm still holding W, which means that next frame we're going to be accelerating. And we're accelerating in this direction. Whoops. We're accelerating in this direction, which means that a little bit is going to get added to the top, which will shift the angle of our velocity to be back into the wall. So now we add a little bit of acceleration from holding W, which shifted our velocity angle. Which means that the next frame we're gonna move and immediately hit the exact same spot again. Because we're still tilted and super close to the wall. So we're gonna hit the wall again. And the velocity is gonna get redirected again. So we redirect. Oh crap, oh god. And the velocity gets redirected again, so we have something like that perhaps. But we don't move again. And then the next frame, we accelerate a little bit more. So we go there. And now our velocity is pointing into the wall again. So we move, immediately hit the wall, and then just peace out. And then this just keeps happening. So we're standing next to the wall, and our velocity just keeps being nudged a little bit towards the wall, which makes us hit the wall immediately and then never moving. So that's fair. That's okay. That's a fair analysis. But what happens if I just don't accelerate then? Shouldn't that work? Like if I release the accelerate button right before I hit the wall, I still get stuck. So what's up with that? Shouldn't that work? Because then we wouldn't have the acceleration the next frame. So then this, this sort of angle change of the velocity shouldn't happen the next frame. Well, the problem is our differential friction. Remember that we used a different friction for forwards and sideways velocities. So that our sideways velocity is always shrinking much, much, much faster than the forwards velocity. So that means if we have this velocity in one frame, so let's just draw the total velocity that's going to be if we add them two together. Let's add these together. Our velocity is going to be something like that. Then we apply friction, which means maybe the sideways velocity shrinks by quite a lot. Maybe it goes to something like that. So we're shrinking down the sideways velocity, but the forwards velocity barely shrinks at all. It kind of stays almost the same as it is. And that means that after we applied our friction, the angle of the velocity has changed. So now you can see there's an angle difference here. So the velocity will always tend to turn towards our forward direction. Because the sideways one will kind of go away fast, and then all we're left with is the forward vector. And as you can see here, our forward vector is pointing into the wall, which of course means, since we have this sort of perpetual turning, where our velocity is always kind of turning towards our forwards, that means that this velocity vector is going to turn a little bit towards our forward vector, which will take it into the wall. And we have the same problem. And this is kind of like, it might seem a bit weird. Like, why would we turn just by friction? But of course, this is how cars turn, right? Like, if you twist your wheels, like if you turn your wheels, suddenly the friction differential on your front wheels will be different in that it will be preferable for the velocity. It will preferentially select velocities that are aligned with the wheel, because that's where the friction is very low, versus the velocities that are to the perpendicular of the wheel. So those velocities will very rapidly go down to 0, while the ones alongside the wheels will stay. So that means you can turn the car, because you can sort of steer with your front wheels where you want your velocity preferential to go, and that's how you steer. Kind of oversimplified, obviously, but I'm not a fucking car mechanic, okay? I don't know what cars are even. You could show me a bike and talk me into it being a car. So yeah. So that's the problem. And both of these problems would be fixed if we did iterative collision solving. Iterative collision solving. Now, this is not the same as substepping, which is something you probably heard. This is not the same. So iterative collision solving is not the same as substepping. They're different things. You're right. And the way that iterative collision solving works Man, I'm running out of space. Okay. The way that iterative collision solving works is that we take that remaining movement into account. So when our car is moving, we have this whole frame delta, right? We have this like, okay, this is how much we're supposed to be moving. It's the delta. Whenever we hit something, so right now we moved like a little bit. Move to like here. We hit the wall. And then we look at, okay, at what time in our move delta did that happen? So if this whole delta movement represents a time, so let's say we're kind of like, okay, one frame took 60 milliseconds, let's say that. Let's say 100 milliseconds, actually, that would make things a lot easier. So one frame took 100 milliseconds. That means we're responsible for simulating 100 milliseconds of movement. Like we have to kind of catch up to that 100 milliseconds to accurately represent what would have happened if that was just continuous, right? So then we see, okay, this crash here happened after 10 milliseconds, let's say that. As in, it happened after 1/10 of the delta we wanted to move. That's where we crashed. So in 1/10 of the distance, we hit a wall. So that means 10 milliseconds, like 1/10 of 100, has been accounted for. This distance here is 10 milliseconds of the simulated time. So we shove that off. So now we have 90 milliseconds left to simulate. So then we do the redirection. So we redirect this delta to be what it should be along the wall. And then we want to travel the rest of the way. So we want to travel an additional 90 milliseconds. Kind of seems weird to say that. Like, okay, what does traveling 90 milliseconds mean? Like, that's a measurement of time and not a measurement of distance. And yes, it is a little bit confusing, but hopefully we can get through it once we actually start writing this. So now we want to travel the remaining 90 milliseconds. So then the car is gonna move over to here, and hopefully we don't collide on anything until we get there. So now we can see that we have simulated the 100 milliseconds that we needed for this frame. 10 of the milliseconds took from the start to hitting the first wall, and then the remaining 90 milliseconds took from that point to getting over here. So now we've accounted for the whole 100 milliseconds. And then there might be another collision in there, so you know, maybe we hit another wall here or something. And then we have to account for that, like this hit here, and redirecting that and moving the remaining maybe 20 milliseconds or something after that hit, and so on. And that's why it's called iterative collision solving, because you're sort of iterating through all of these steps. Like, do a step, we hit something, do another step, okay, we hit something, do another step, until you run out of time. Until you've accounted for the full frame time. So that's iterative delta solving. Or iterative collision solving, sorry. Because you're iterating through all of these steps. So that's what we're gonna do.
Does the hit result save and contain a big part of the vector we couldn't move?
Yes, or kind of. It contains the time, which is very good. So it contains like where in the delta did you actually hit something. So that's good. So that's what we're gonna use. So iteration time. So then what I'm gonna do, I'm gonna rewrite this function a little bit. What I'm gonna do is that I'm gonna make a remaining time variable. Whoops. So remaining time is gonna be how much time is left for us to account for. And of course, by default, that's gonna be delta time. That's just gonna be like the time it took from the last frame to this frame. So that's gonna be, yeah, how long we have to move. And then we're just gonna shave that remaining time off as we hit something. So we're gonna do a while loop. While remaining time is less than, or sorry, is bigger than 0. Then we're gonna do a sweep. And of course, we don't want to sweep with velocity times delta time. We want to sweep with velocity times remaining time. All right. And then we want to check if we hit something. We're gonna redirect the velocity, and then we're gonna shave off how much time did it actually take to get there, to get to the hit. And we can get that by hit time. Now this time, we're gonna have to be a little bit careful here. Time here does not mean time in milliseconds or seconds or anything like that. Time is a number from 0 to 1, meaning 0 means we hit something immediately, like we couldn't move anything. And 1 meaning we moved the entire distance, and just at the very, very, very end, there was something that we hit. And then 0.5 would mean, yeah, right in the middle we hit something. So that's sort of the percentage traveled before we hit something. So we're just gonna shave off remaining time based on that. So remaining time minus equals remaining time times hit time.
Wait, what did hit time do?
Hit time is the percentage we traveled before we had a hit. So in this case, like if this is the 100% distance, right, the whole delta we send in our case it's the thing we put in to add active world offset here. So this is kind of the delta in this case. Time will be where percentage-wise, where the beginning would be 0 and the very end would be 1, where on this line did we encounter a collision. And in this case, where we hit here, we traveled this distance. And that would be, yeah, let's just say that's 0.1. So we've traveled 10% of the full distance before we actually hit something. Does that make sense?
And that's delta location.
Delta location. Yeah, that would be this, yeah. Or is that what you mean?
Yeah.
Yeah, exactly. So this this distance here would be the delta. This would be passing here. The word time is a little bit confusing. I will say that. The word time is not very helpful. Maybe like percentage traveled would be a bit better. Or something.
Yeah, because it's like the percentage of time that's gone, right? It's not like...
Yeah, exactly. Exactly.
It's not time.
It's not time in seconds. It's, yeah, a percentage. So that's why we do the remaining time minus equals remaining time times hit time. So, like, the full distance would be remaining time if we're thinking, like, okay, how much time does this delta actually, like, what does it mean time-wise? It would be remaining time, since we're doing velocity times remaining time here, sorry. So that means if we hit something at 0.5, that means we travel, if this whole thing is 100 milliseconds, yeah, take a shot. Yeah, I'm realizing that this would be incredibly confusing. Yeah, if we got a hit time of 0.5, that means we travel half the delta, and the real time, the remaining time that represents, would be half of 100 milliseconds, so that would be 100 times 0.5. Which is equal to 50. Actually, that. Yeah. So just hang in there. It's fine. You're doing great. So now we're shaving off the remaining time if we have a hit, right? And if we don't have a hit, that means we just travel the entire distance without hitting anything, which means we're done. It's like, okay, we didn't hit anything, we're done here. Like, there's nothing more to move. So then I'm just gonna brake. So we don't need to do anything. Alright, so let's try it. I don't see what could fucking possibly go wrong. Yeah, we have a while loop that we might never exit out of, but that's fine. I don't think that's gonna happen. So if we make a wall. Okay, guys, I need you to hold your breath here. Pray for me. Let's go! Hey! Oh. Oh no. It froze.
It crashed.
Well, it didn't crash, but if I brake here, so I'm just gonna hit brake all. That's just gonna force break the code wherever it's executing right now. Of course, we broke in some thread sleep stuff, but I'm just gonna see. I'm gonna go to threads, So here's all the threads running right now. There's a billion of them. Unreal does a lot. And I just want to go to this main thread. So I'm just going to go there. And let's see, threads. No, not threads. Sorry, call stack. Wait. Oh, okay, yeah.
And how did you get to the call stack and the threads?
You just click call stack here. If you don't have it, then it's a debug, Windows, call stack. Call stack is probably the most useful debugging tool in Holo Visual Studio. Like if you have a crash that I'm helping you debug, like 9 times out of 10 I just want to see the call stack the first thing I do. So the call stack is quite huge right now because we broke in like anywhere, so it's just gonna break in some random deep function. So if I just walk up the stack here, we should find here is raise car movement component tick. So if we just go there, we can see that yeah, we're stuck in this while loop here. And I do actually think I know what's wrong. So if I break here, if I just put a breakpoint here instead of doing break all and then F5, we can see that it just constantly, it just like iterates forever and never gets out. So it just keeps iterating. It's always finding a hit somehow, and no matter how many times it tries to redirect out of the hit, it just gets stuck.
Do you know where we can find the call stack on Rider?
No, I have no idea. I think it's like in some it's just like a general debug window, and I think in there's a call stack. I believe so. Do you remember, Johanna?
Thanks for nothing.
Okay, Daniel. Fucking careful. Johanna, do you remember where the call stack was? She's not even here.
Did you just call me Daniel?
No, I forgot. Sorry.
No, wait. Oh, that's not Daniel. Oh, it's Niklas.
Oh my god.
Sorry, Niklas. Sorry, you sounded like Daniel for some reason.
I'll find out where you live.
Oh, no. Not you too.
And I'll come and sleep with you in your bed.
Okay. All right. Let's let's travel away from this topic and go to go to something else. So yeah, okay, so yeah, what I was thinking is actually true. So if we look in the hit, I'm just gonna hover over the hit here. Boom. We can see here a B start penetrating boolean here. And that's set to true. And what B start penetrating does is that when you began the trace, or when you began the sweep, you will already inside of something else. So that would be like if we have the wall here and we're the car, and the car is already kind of sticking into the cube and we're trying to move out of it. Like, it doesn't matter where we're moving. What's gonna happen is that it's gonna try to sweep, but it's like, oh wait, there's something immediately inside of you already. Like, I can't sweep out of it. And then it says, okay, just return with B start penetrating. So that's what that means. And you know, I remember we talked about this, right? We talked about this in SDL, that we didn't have any sort of depenetration logic for our game. And this is where that starts to become important, because the physics on its own, just the math, the collision math, is just not accurate enough to guarantee that we're never gonna accidentally go inside of something. So even though we're doing sweeps, like, you know, in theory a sweep should never put us inside of something. Like, even if we sweep, we should just like go, so we just touching the thing. Like it should move us like essentially as close as it can without touching. It's never guaranteed that that's gonna actually happen. It's gonna try, and most of the time it will work. But sometimes due to like, you know, floating point imprecisions and so on, there's so many places of failure that at some point it's just gonna happen that we're gonna just end up penetrating something. So that's just a sort of a reality of these collision APIs. So the way you mitigate this, we won't do it because I don't think we really need to, but I can tell you how we do it in at Hazelight, just for interest, I guess, like just to give you a picture. The way you do that normally is that you do something called pullback. So if we have our little guy here and we're sweeping, and the collision system tells us like, oh, we hit here, like the location of the sphere was here when we hit. So that's the location where we're just touching. The way you would solve this or mitigate this penetration issue is that you will pull back the hit just a tiny bit. So you would actually not take exactly where it says. It will actually walk back a few units. It's usually like, I think we did maybe 1 unit or 0.5 units in it takes 2. I don't quite remember. So we actually pull back a little bit just to give a little bit of wiggle room in the calculations so that you don't end up start penetrating all the time. It's not this extreme, like this was quite an extreme pullback, but you get the picture. So that would be like the solution to mitigate this kind of start penetrating issues. But they won't make them go away. They will still happen in extreme cases, like if you're coming at it at a very shallow angle. Like when we're coming at it like a super shallow angle, and the hit was like here. Then it doesn't actually matter that you're pulling back by 1 unit. Since it's such a shallow angle, that won't actually change your location that much compared to the wall. Like you'll still be incredibly close to the wall, so these issues will still kind of pop up. Because you're not pull backing 1 unit away from the wall. You don't want to do that because that's going to cause a bunch of other issues. You want to pull back in the direction you came from. So that means if you're pulling back 1 unit in the direction you came from, sometimes you move far away from the wall and avoid penetration. Sometimes you're going to move not very far at all. And then penetration issues are still going to come out of it. Yeah, so that's pullback. Well, we're not going to do this because fucking whatever. What we're going to do...
But is pullback and depenetration, are those the same thing?
No, depenetration is when you're just like, oh, we fucked up, we are penetrating. Pullback is to avoid penetrations happening in the first place.
Oh, okay.
Yes, so it's like a mitigation tactic. Alright, so what happens when we're penetrating? Because that's always going to happen. There's no way to avoid that, really. So what happens? Well, it's actually quite simple. In Unreal, we get 2 variables to help us out. First of all, we have the stop penetrating variables. We know when we are penetrating. And then we have here penetration depth. And that is how deep into the thing we are. So that would be like this depth here. So that's how deep into the thing we are. And then whenever we are penetrating, the normal will be reused to be what is the shortest direction out of the thing. So when you are penetrating with something, the normal will become what is the shortest path out of here, or the shortest direction out of here. So most of the cases those will be the same, but in some cases they won't. So the normal will point sort of in this direction here. So the normal times the penetration depth, normal times penetration depth, will give us the shortest depenetration vector. So that is the vector we have to move by to get us out of the penetration. And that's called something. I know it's like MVP. I know it's called MVP. But I don't know actually what it stands for. It's like minimum vector or penetration or something. Something of probably those words or something. So you might see like calculate MVP. You might see those functions thrown around to be like calculating what you should move to depenetrate. But we get those for free out of the hit result. So we're just gonna do that. So we're just gonna do if hit be start penetrating. God. Then add actor, owner, add actor, world offset. And we're gonna do hit normal times hit penetration depth. Else do this thing. We don't have to worry about time, since if we're penetrating, that means the time will be 0 because we started penetrating. We didn't have the chance to move anything, so we don't have to worry about reducing time here. The only thing we need to do is just get out of there. Yeah, maybe use dot product and have a higher offset if it's a lower angle. Yeah, that is what you do. But in the end, if you were pulling back enough so that you have sort of a big distance between you and the wall, you would be pulling back too much. So you would be it would be quite visible that you didn't actually move the entire distance. So you want to be careful with pulling back a little bit too much. But yes, usually it is dot product to kind of figure out how much we should pull back. It's not just a flat value. So, right, now we have depenetration. It's looking a bit bad. It's better than a crash though, right? Well, it won't crash, but you'll just be penetrating. So, whoa, depenetration time, baby. Otherwise, just redirect and keep going. Okay. Okay, so we can move at least, so that's good. So let's put a 1 in here and see what happens. Whoops. Guys. Fuck. We got so close. We got so close. And then I fucked it up. Okay, what's going wrong? Okay, so we are penetrating. Okay, so we're never actually getting depenetrated. So what's the penetration depth? Whoa. That's not good. What's the normal? Wait, is it just optimization stuff? Whoops. Oh,
I think Unreal actually did crash for me.
Oh, fucking close it down. It did crash?
It stopped responding somehow.
Well, that probably means, yeah, you got stuck in an infinite loop. Just like me. Let's try that again. Whoops. So yeah, the problem, I saw that in chat actually, someone said it. The problem is that we're not sweeping at all with rotations. So if I actually rotate into the wall, we'll start penetrating. So if I do this, if I like kind of go alongside it and then just kind of rotate into it. Fuck, I missed. and rotate into it. Oh, it's so hard when I can't rotate when I'm moving. So let's see. Let's just go up and then rotate. Crap. And rotate. There we go. So I rotated kind of my back wheel into the wall there. So let's see then. Yeah, so we're definitely always penetrating. And then let's check what the hit is. What the fuck? Hit? Has it been optimized out? Oh, okay. Okay, yeah, so the penetration depth is just super tiny. You see it's like 9.999 and then it's like e to the minus 0.5. So it's like a super tiny penetration, but it's still kind of counting that as a penetration. So I think here we have the same problem, where sure we're moving out of it, like we're using the minimum depenetration vector to kind of move out of it, but it's just not accurate enough to actually get us out of it. Like the floating points just aren't that granular, so we're still getting these issues. So what we're gonna do is that we're just gonna add a little bit of padding to the penetration, to the depenetration. I mean, sorry. So we're actually gonna do hit.penetration depth plus 0.1. Use a tiny value, just to really make sure that we get out of the wall. And yeah, it kind of makes sense because like when you're talking about penetration depth, they are in like the 0.000009, and our position is kind of big, like our positions are in the thousands. Then it kind of makes sense that the floating points at that point just aren't granular enough. When they're that big, they aren't granular enough to handle those kind of really small distances. So it just ends up not doing anything.
So this is 0.1 to the penetration depth. That fixes the rotation issue, like the.
Well, hopefully. I mean, it will still be penetrating when we're rotating, but hopefully whenever that happens, it just pushes out again. So as soon as we rotate a wheel into the wall, we should be like, oh no, we're start penetrating, and then we should depenetrate and then keep moving. So it shouldn't cause any problems. It should just kind of look a little bit weird.
Do many games use that sort of thing where they push you out of the wall, they penetrate?
Yes.
Because I remember seeing in games where you like shake along the wall because that might be depenetration then.
Yes. It's a super common thing in collision. Let's see if I can get us stuck here. Well, it seems to work.
Mine froze instantly.
Instantly. Let's see if I can get it to freeze as well.
If you drive head on, like no rotation, does it handle that as well?
Yep.
Oh, yeah. It didn't for me.
Oh, I did it. Okay, well it seems to work now. I could probably get it stuck in some like weird situation. Like I can probably just make a level that will make sure to get us stuck. But at least for me this seems to work fine. Johanna, I think your problem is that you need to make sure to wrap these in parentheses. Because otherwise you're gonna get hit normal times penetration depth, and that's gonna be a vector plus 0.1. And if you add a scalar to a vector, you will actually add all of the components, which I think will give you some issues. But yeah, so it seems to work for me. I'm gonna help you guys debug a little bit. But yeah, seems like we got some basic collision stuff working. So isn't that neat? I was thinking actually for fun, just for fun, since It Takes Two is kinda open source, kinda. Like the whole InduScript code is just kind of available. It just gets downloaded to your computer when you download the game. I was thinking like maybe it could be fun to actually look at the collision solving code there. I used a little bit just to see the similarity of what we're doing here compared to what we did in It Takes Two. I thought it could be kind of interesting a little bit. We won't spend too much time on it, but just a little bit, just for fun. So let's open that up. There it is. So here's like the entire AngelScript source code for the game, which is quite nice. It's been made it very easy to mod. So a lot of people have modded the game for speedrunning, stuff like that. It's been very cool to see. And since like I think 95% of the game is written in AngelScript, and then the remaining 5% is sort of a split between C++ and Blueprint. That means like there's really not much in here that you can't find in AngelScript. But so if we go to character collision solver. Oh yeah, I forgot about my diagrams that I made. Dude, I was so fucking proud of these like ASCII diagrams that I made. Yeah, we spent like months and months on this shit. So yeah. So here's like redirection. So you can see like there's a bunch of stuff related to the redirection. Like, are you on a wall or on an invisible wall? Apparently, are you on the ground? Blah blah blah. Here's the step up code. So here's the code for doing a step up. Here's a step, yeah, and then a sweep downwards, yeah. And here's like the edge cases we were struggling with. Like, what if your capsule is like slightly off the edge of the target surface, and then we have to handle that, and stuff like this. It was very, very fun. It was super fun to work with. Let's see if I can find the actual loop though. Oh yeah, no, we moved that to C++. Okay, never mind. Oh, I was hoping we would find like the actual for loop that we made today. But yeah, so it's like there's so much work when it comes to making like a platforming game that we just don't have to worry about. We won't worry about it. But yeah, that's why it's like if you're making simple movements, like, you know, with this top-down car game, then it's totally fine to make your own movement code. But then, yeah, if you're gonna move into doing this kind of stuff, then perhaps you want to use Unreal's default one. And we also had the depenetration solver, which I didn't work on this, but I know it was a lot of trouble. So you can see, like, it's once you have more complex levels where there's a lot of crazy geometry that you can sort of get stuck in, then it becomes MTD. That's what it's called, MTD, minimum trans dimension. I have no idea what MTD stands for. But that's the depenetration vector that we were talking about. So you can see that there's a lot of things going into actually depenetration something. Yeah, here you can see here's the while loop for. So they're doing an iterative depenetration there, which is quite cool. Unfortunately, I don't know about this. I should really research this. I wish I was there when he wrote it, but it's very cool stuff. So yeah, I mean, what we're doing right now, it really isn't really that different from what we did at It Takes Two. Of course, just that It Takes Two is crazy complicated because there's just so many more cases that we have to handle. But in the end, it's like iterative collision solving, redirection, and depenetration are like, you know, the main things that you always do. Minimum translation distance. Maybe? Distance, it's a vector though. I don't know. I could Google. I could check, but it's kind of funny that I don't know, so I don't. But yeah, we could also write our own like for ice skating, for example. Like I could make my own collision solver just for ice skating, just so that I could do some custom stuff. I think here, yeah, I'll write step down, and if a surface was walkable or not. So that I could do some custom collision checking just for ice skating. So we could do that, which was quite nice. I think our movement system was really, really good. It's pretty cool. Pretty cool. So that's that. Well, that was a crash course in collision solving and iterative stepping and whatnot. Thanks, David. God, I worked so hard on that fucking ice skating. It was supposed to be like just a little small thing you could do in the cities. Like, oh, wouldn't it be nice if you could like skate around? Wouldn't that be sweet? And then it just turned into this fucking like, what if there's a mountain and you can like jump through hoops? And there's this whole fucking thing, and it just grew beyond fucking. It grew to this monster that just took ages, but it was a good time. Yeah, Snow Globe was objectively the best level. Anyway, so that's it. I'll stick around to help people with their issues, but otherwise this class is adjourned, so you can go sleep. But so thank you for today. I thought today was actually really fun. I had a really good time. So I'll see you guys back on Friday, and let's do some cool. Let's do some mechanics then. Maybe do a checkpoint system or something. Maybe AI. It would be really fun. Maybe some guns. And yeah, see you then. Thank you. Bye bye. Okay, I did work on I did work on a way out as well, actually, and I didn't do as much there, but.
By the way, who did the collision code? I mean, not all of it, maybe, but like that part that you said you weren't there to see who wrote it.
Well, the collision code I did together with another coder. But then the penetration stuff, that's the other code that did that part. But yeah, so we together made the character collision solving, which was very fun.
But looks like the collision code just ballooned out of control.
Yeah, well, that was kind of the problem, where he wrote a really simple one in the beginning, and then it just didn't hold up once we had more like crazy movement that needed to work. So it just kind of didn't hold up. So then I was like, okay, let's just rewrite it from scratch. So then we sat down and did that. And we actually ended up rewriting it 2 times because the second iteration didn't really work either. So we had to rewrite it a 3rd time. But yeah, so there's so many edge cases all the time. Like we would write something that we thought was like, this is bulletproof. And then 2 days later, the designer would be like, hey, I'm getting stuck here. And it's like, fuck. So we had to go through and fix that case as well. And it's just like continuously like that up until we ship the game. And even now, when you play the game, there's still plenty of places where you sort of get stuck on weird geometry and stuff. Because that's just kind of the way it is. Okay, anyone who needs help?
Right. Can I ask a question related to that? Because
yeah.
This was one of the issue, like a little bit of a issue we had in like GP2 as well. Because but how much would you work with like the artists or like the level designers to like prevent those kind of like edge cases? If you know what I'm asking.
I understand what you mean. It was a case-by-case basis for sure. It was the kind of thing where when we went and looked at the geometry, we kind of looked at it with the designer and asked, like, is this a common thing? Like if it's just like a random hole in the geometry, then obviously it's like, okay, can you cover up that hole? Or if there's some weird pinch or something. But sometimes it would just be like a weird wedge, like a wedge that we just didn't really think about. And we asked them, like, is this a common thing to do? And they're like, yeah, I'm just building the level and it just turned out like that. Then we're like, okay, there's no way we're going to be able to police that. There's no way we're going to be able to go through every single level, every single asset and make sure there's no wedges in there. So then it's just kind of like, okay, then we just have to make that work. But if it's something like we look at the collision, it's like we've never seen this before in any other level, and the designer and artist agree that it's just kind of a weird collision, then they would just fix that and just cover it up. So it was really like a case by case basis. But then that's why we're nearing. So
like sometimes like the level designers would like change the level so that it wouldn't be like that.
Yes, sometimes. Then at the end, whenever we had collision bugs near the end, then it was like, okay, it's way too late to fix bugs now in the collision in this, because every bug we fix is just gonna potentially introduce new bugs. So then it just became like, if there's a collision bug, no matter what it is, just cover it up, like just fix it right in the level. But up to that point, it was kind of like we choose kind of what we wanted to support or not.
Okay, that's interesting.
Yeah, but yeah, in general, Hazelight is a very tight communication between all departments, like artist, animation, design, and code. Like, we really work tight knit together and talk a lot. It's very good.
But would there be, maybe in some kind of bigger mega AAA company, would there like be sort of rules for level designers, like what kind of like how does the movement work, and then like the level designers would have to know those sort of rules and then not do stuff like that, or is that a fantasy in my head?
In AAA, I would believe it's something like that. Yeah, it's definitely wouldn't be you just go and talk to some guy like we do at Hazelight. It would most likely be, if there is a serious bug, then you would like bring it up to your lead, and your lead would talk to the programming lead, and then it will be like a whole discussion thing. So it would probably just be easier just to cover it up. But that being said, I have never worked at a AAA company, so I'm not too sure, but that's my impression from talking to other people who have worked at DICE and stuff. That they just follow whatever happens kind of mentality.
Thanks.
Yeah, no problem.
Why do these functions end with const in this code? Many of them have like const at the end.
Yeah, so that was because we wanted to have a system where we could the solver should always be what do you call it? Deterministic. So if you put in some data, if you like solve this delta, then we always wanted the same result back out. So that's why we added const there, so that we could never change any variables on the actual solver during a solve, so that like, you pass in the data once, it changes some value, and then the next time you send in the same data, you get like a different result out of it.
Yeah.
So that's kind of why we added const there, because then we could do cool stuff, like we could record a bunch of frames, so we could play until we find a bug, record, and then we could go back in time and actually like debug every frame to see like what went wrong, like what happened this frame, like what the redirects did we run into and so on, because we could just rerun the Iterative with the collision solver with the same input on that frame, and it worked out really well, and it helped us a lot to solve bugs and stuff. So that's why they're const.
How much time did it take to just do this collision code for the game to work?
I would say like maybe
how many months?
6 months, I would say, in total, something like that. 6 months of this working together every single day. It's a lot of time. Of course, it was staggered out. Like, it was like, we rewrote it in like 2 months, and then it was like maybe 1 month of debugging it and fixing bugs, and then it will be like every other day we fix a bug or something. But yeah, a lot of time, because it's like the core of the game, right? It's like it has to work really well, because that's what you're gonna be doing the whole damn game. So it really needs to stand up. So it was a lot of work. That's why we commented everything so rigorously, because we never wanted to come back here and don't understand like what does this do, like what edge case is this fixing. Like, we wanted to leave comments there so we remember like, oh yeah, this thing was to fix that one edge case, right? So that's why we commented it so rigorously.
Yeah, I definitely like that you commented the code.
Yeah, that was good.
How important is it to be able to write your own sort of collision detection stuff like this, like in a general game development sense?
I mean, not very. It's the sort of thing that's good to know how it works. Like, you don't have to have written it like rigorously. Like, I probably won't do this again, maybe, unless maybe I'm working on some other game, small game or something. But I mean, the same could just go for essentially anything. Like, how important is it to make a gun? It's like, I don't know, it depends on if you're gonna make a gun or not. It's just kind of like, this stuff made me very good at math and made me very good at understanding how physics works, how collision works. So it gave me a lot of skills that I had that is usable later. But the act itself of writing a collision solver, that's not that everyday thing for sure. You might go your whole career without ever having to write one, but sort of thing that's just good to know. And I just love talking about it. I just think it's so fun and so interesting, and I just love talking about it, and I love teaching this stuff. So that's why I'm just very passionate, guys. All of this work.
But you said you learned how to do collision doing this, right? Or you learned a lot of physics and collisions, so that means you didn't like teaching this before that.
No, before I didn't know about it. Before I did this, I didn't know all that much about like how the penetration and all that shit works or iterative collision solving is. I had to learn it working on this. We kind of learned stuff together. So that was very fun. It's always fun when I'm working on stuff I don't know. That's where I think I'm always the most happy when I'm just given a task that is like, I have no godly clue how to do this and I just have to figure it out. That's where I'm like the happiest. That's where I thrive.
Wait, are you still working at Hazelight?
No, I don't work anywhere.
Okay.
Unemployed, baby. Let's go.
That's the life.
Yeah, that's fucking sick.
The
life.
dream.
Yeah. You sit at home, teach kids, tell jokes, and make money.
Yeah, flip off people on the streets.
Yeah. Yeah, fucking worker drone. What are you, fucking lame-o? Yeah, that's what I do.
Awesome.
That's what life is about. But yeah, we might go through it. I think I'm gonna have a course I had this for FG20 at least. Not a course, but like a few lessons on AnyScript. Just because it's interesting if people want to work with AnyScript. Like, it's so much faster. Like, you don't have to recompile. It's just like in Unity. I would say it's even better than Unity. You just hit save and it just works. Like, you can even do it while you're playing. Like, while you're playing the game, you just add some functions and change some functionality, hit save, and then you can just keep playing and it just recompiles. And it just works so good. Like, it works so amazingly well. So that's kind of why I like doing a course or something. So then we might just go through a little, like, check out some systems in It Takes Two just for like examples and stuff. Like, here's the sap count, for example.
Is there like some background magic that makes it work, or just work when you save?
Well, of course, yeah.
Script.
I mean, there's this whole. There was Lucas at Hazelight. He's the one who made everything work. He was just like, we need a scripting language that's actually good, and he was like, I'm gonna use the AnyScript, and he just implemented everything in like I think it was like a year or something. So he's the magician who actually made all of this happen, and it's super nice. And he's such a fucking talented guy. It's insane. So yeah. Well, that's it. I'm not gonna keep you guys too long. So let's head off.
Emil, would you mind looking at my collision thing for?
Oh, yeah. Of course. Yes, let's do that. Sorry, I got distracted. Yeah, good memories coming back to me. Let's see.
So I think I did the same thing as you, but if I drive into something head on, it just freezes.
Okay, let's check it out.
So if I just drive right into this wall, the game just ends.
Big freeze. Okay, let's. Okay, so put a breakpoint in. Put a breakpoint in.
Here.
Oh yeah, did you shut it down? Oh, you did.
Yeah, I had to task manager.
Oh, okay. You can use Shift F5 in Visual Studio to kill it.
Ah, awesome.
Yeah, that's a little pro tip for you. So don't add a breakpoint yet. Add a breakpoint when you're frozen.
Right, makes sense.
So now let's put a breakpoint and see.
So,
All right. So if you one more. Yeah, let's check out the hit now.
yeah.
Let's see what the hit is. So time 0, distance is 0.4. You're not penetrating, so it just seems like a hit immediately.
Yeah.
Oh, you're not assigning velocity, that's the problem. So you gotta do
right,
velocity
here.
equals the vector plane project, that's why.
Alright, okay. Yeah, I was thinking if it was like I thought it didn't like return, it just modified.
Yeah. Yeah, it's an easy mistake to make. Alright, let's try
Yeah,
it. Let's
yeah.
try it now.
Well, that should probably.
It should work now, I hope. Otherwise, I will look dumb.
It works.
Yay! Easy.
Awesome.
Alright, sweet.
Thanks a lot.
Yeah, no problem. Okay, anyone else before we call it a day? All right.
I'm kind of shocked that my code actually works without any issues.
That's damn, you're getting better, dude.
Yeah.
You're improving. All right, guys, thank you very much.
thank you.
Have a fucking POG afternoon, and I'll see you guys on Friday. So
Same. See you on Friday.
bye-bye.
Thanks.
Bye.